Welcome to our deep dive into the fascinating world of simple harmonic motion. Um, SHM for short.
SHM.
Yeah, you've sent us some really great educational resources on this topic, and we're going to break down some of the key ideas so you can start seeing SHM in action all around you.
Yeah.
Ever notice how some things in nature just have this back and forth rhythm?
Yeah.
That's SHM at play.
Yeah, what's so fascinating about SHM is that it's governed by a pretty simple principle.
Okay.
The further an object is pulled away from its resting position, the stronger the force trying to bring it back.
So it's like a cosmic game of tug-of-war.
Exactly.
Yeah.
And that constant push and pull creates the oscillation.
Right.
We can actually describe this mathematically
Like
with
that.
what we call the defining equation of SHM.
Okay.
A equals negative omega squared x.
Okay. Now, I know equations can sometimes feel a little intimidating, but
Right.
this one is actually pretty straightforward once you break it down.
Yeah.
Walk us through it. What are we looking at here?
You got it. So this equation tells us that the acceleration of an object undergoing SHM is directly proportional to its displacement from what we call the equilibrium position represented by x.
Okay.
But there's a twist.
Okay.
The acceleration always acts in the opposite direction to the displacement, hence the negative sign.
So if an object is moving to the right, its acceleration is trying to pull it back to the left.
Exactly.
That's what creates that back and forth dance.
Precisely. And that omega squared in the equation that represents what we call the angular frequency squared, which essentially dictates how quickly the oscillations occur.
Okay.
Think of it like the tempo of a song.
Right.
A higher frequency means a faster beat,
Uh-huh.
and in SHN, it means faster oscillations.
Okay. Makes sense. Now, you mentioned a classic example of SHM earlier.
Yes.
What was that again?
The horizontal spring mass model.
Okay.
So imagine you have a slinky.
Okay.
That's our spring.
Yeah.
Essentially attach a weight to one end, and you've got your mass.
Okay. I can picture it.
Okay, cool. Yeah.
What happens next?
Pull the mass to the right and let go.
Okay.
The spring, like a stretched slinky, wants to snap back to its original length.
Right.
That's what we call the restoring force in action.
Okay.
And it pulls the mass back towards the equilibrium position or its resting point.
But doesn't the mass keep going like it has momentum, right?
You're absolutely right. The mass overshoots the equilibrium point, compressing the spring. Now the compressed spring pushes back, sending the mass in the other direction, and the whole cycle repeats.
So the further the mass is from its resting point, the stronger the spring pulls or pushes it back.
Exactly.
And that's what determines the acceleration.
Exactly. It all ties back to that defining equation we talked about.
Right.
Now, there are different ways this oscillation can play out depending on where the mass starts its journey.
Okay.
Let's dive into those specific scenarios.
Lead the way. What kind of scenarios are we talking about?
Let's start with what we'll call case one.
Okay.
Imagine the mass begins at its resting point, the equilibrium position. In this case, the equations describing the motion involve sine and cosine functions.
Those always take me back to trigonometry
I
class.
know, right?
Yeah.
Don't worry, we won't get too bogged down in the math.
Okay.
The key here is understanding that these equations help us track the position, the velocity, and the acceleration of the mass as it oscillates.
Okay, so case one is all about starting at the equilibrium position. What about case two?
Case two, the mass starts its journey at the maximum displacement, the furthest point from its resting position.
So it's like pulling that slinky as far as it can go before letting go.
Exactly. And again, we have specific equations for this scenario.
Okay.
Also involving sine and cosine, but with a slightly different setup because our starting point has changed.
Okay, now you mentioned earlier that we can verify these equations mathematically.
Yes.
What do you mean by that?
Well, the beauty of physics is that we can test our theories using math.
Yeah.
So by substituting our equations back into that defining equation, A equals negative omega squared x, we can confirm that they accurately describe the motion in both case one and case two.
So it's like a mathematical proof that our understanding of SHM is on point.
Precisely, we can have confidence that these equations can predict the behavior of objects undergoing SHM.
Right.
But, equations are only part of the story. What's really cool is seeing how all this connects to the real world.
That's what I'm excited about. What are some examples of SHM we might encounter in everyday life?
Well, think about a playground swing.
Okay.
As you swing back and forth, you're experiencing SHM.
Okay.
Or how about the pendulum in a grandfather clock? Its rhythmic ticking is another example.
I always wondered how those clocks stayed so accurate. It's all thanks to SHM.
Exactly. But there are even more subtle examples of vibrating tuning fork, the sway of a bridge in the wind.
Oh.
These are all objects oscillating back and forth around a central point.
Wow, I'm starting to see SHM everywhere now. This is definitely making me think about the world in a whole new way.
And we're just getting started. There's so much more to explore in the realm of SHM. from understanding energy to examining how damping affects oscillations.
Before we get too far ahead of ourselves, let's take a moment to just soak in what we've covered so far.
Yeah.
We've got the defining equation, the spring mass model, and even a taste of how SHM shows up in everyday life.
Yeah, but this is where it gets really interesting. We're about to explore how SHM helps us understand and even engineer some pretty amazing things.
This is why I love these deep dives. We're about to connect the dots and see how these seemingly abstract concepts have a real impact on the world around us.
Absolutely.
I can't wait.
Yeah. You know, one of the most fascinating things about SHM is how it pops up in situations you might not expect. Like, did you know that engineers actually use these principles when designing buildings,
Really?
especially in earthquake-prone areas?
You're telling me those towering skyscrapers are secretly doing the SHM dance?
Well, not exactly dancing, but the concept is similar.
Okay.
Think about it, when an earthquake hits the ground, shakes, and those vibrations can transfer to buildings.
Right, and too much shaking can be disastrous.
Exactly. So engineers use their knowledge of SHM to design buildings that can actually withstand those vibrations.
Okay.
They actually want buildings to sway a little bit in a controlled way to absorb some of that energy from the earthquake.
So it's like they're turning a building into a giant, well-behaved spring.
You got it by understanding the natural frequencies of a building, kind of like its inherent rhythm.
Right.
And incorporating what we call damping mechanisms, they can help structures withstand those seismic forces more effectively.
That's incredible. It's like using physics to turn a potential disaster into a graceful sway.
Right.
It makes you appreciate the power of understanding these concepts, right?
Absolutely. And it's not just about buildings. SHM principles are also used in designing bridges, vehicles, and even sensitive instruments.
Speaking of instruments, I've always wondered about musical instruments like a guitar string
Yeah.
that vibrates to create sound.
Ah,
Is that SHM too?
you bet. When you pluck a guitar string, you're setting it into oscillation. That back and forth motion creates sound waves that travel to our ears.
Wow, so every time I hear music, I'm actually listening to SHM in action. That's mind-blowing.
It really is. And the pitch of the note you hear depends on the frequency of that oscillation.
Okay.
Remember our tempo analogy?
Mm-hmm.
Faster oscillations mean higher frequency, which translates to a higher pitched note.
Okay, now I'm really seeing SHM everywhere. But before we get carried away,
Yeah.
let's quickly recap what we've learned so far about this fundamental concept.
Great idea. We started by breaking down the defining equation of SHM A equals negative omega squared x, understanding how acceleration is tied to displacement, but acts in the opposite direction.
Right, and that negative sign is key to creating that back and forth motion.
We explored the horizontal spring mass model, a classic visualization of SHM, with the spring acting as the restoring force, always trying to pull the mass back to equilibrium.
We also tackled those different scenarios, case 1 and case 2,
Yeah.
where the mass starts at different points in its journey. And we saw how the math supports our understanding of these scenarios.
And most importantly, we've started connecting these seemingly abstract ideas to the real world,
Yeah.
seeing how SHM plays a role in everything from earthquakes to music.
You know, one thing that's really sticking with me is this idea of natural frequencies. You mentioned that engineers use them to design buildings, but I'm curious, do all objects have a natural frequency?
That's a great question, and the answer is yes. Every object has a natural frequency or even multiple frequencies at which it prefers to vibrate. It's kind of like its inherent rhythm.
So if you apply a force to an object at its natural frequency, what happens?
Ah, that's where things get really interesting. If you apply a force at an object's natural frequency, you can cause it to resonate.
Resonance. That sounds familiar, but I can't quite place it.
You've probably experienced resonance without even realizing it. Remember those old cartoons where an opera singer hits a high note and shatters a glass?
Oh yeah. Is that actually possible?
It is. If the singer's voice matches the natural frequency of the glass, it can cause the glass to vibrate so intensely that it breaks.
Whoa, so resonance is like a superpower for SHM.
Uh-huh.
It can amplify the effects of those oscillations.
Exactly. And while it can sometimes be destructive, like in the case of the shattering glass, we can also harness resonance for beneficial purposes.
Cool, Hannah, picturing those cartoons again. Is this where we get into the territory of using sound to levitate objects or something?
Well, levitation might be a stretch, at least for now, but we do use resonance in a variety of technologies, from medical imaging to musical instruments.
Okay, you've officially piqued my curiosity.
Uh-huh.
Tell me more about how we're putting this resonance superpower to good use.
Okay, so we've got this amazing phenomenon called resonance, where objects vibrate with extra oomph when they're timed at their natural frequency.
Right.
I'm ready for some real-world examples.
Well, one of the most common applications of resonance is in medical imaging,
Okay.
specifically MRI machines.
MRI magnetic resonance imaging.
I've definitely heard of those. But how does SHM fit into the picture?
It's all about those natural frequencies. Again, MRI machines use strong magnetic fields and radio waves to excite the hydrogen atoms in our bodies.
Okay.
Different tissues have different resonant frequencies, and by detecting those frequencies, the machine can create detailed images of our insides.
Wow, that's amazing.
Yeah,
So by understanding how those tiny atoms vibrate, we can create images that help doctors diagnose and treat illnesses.
exactly. It's a beautiful example of how understanding a seemingly abstract concept like SHM can have a profound impact on healthcare.
And what about music? You mentioned that resonance plays a role in musical instruments.
Absolutely. Think about a violin.
Okay.
When the bow moves across the string, it causes the string to vibrate at its natural frequency. But the sound of a single vibrating string wouldn't be very loud, would it?
Probably not. It would be kind of wimpy.
That's where the body of the violin comes in. The shape and construction of the instrument are designed to amplify those vibrations through resonance, creating a richer, louder sound.
So the violin body is like a resonance chamber, boosting those vibrations.
Precisely. And it's not just violins. Many instruments use resonance to enhance their sound, from guitars and pianos to flutes and drums.
You know, it's incredible to think that this one concept, SHM, is behind so many things we take for granted, from the music we enjoy to the medical technology that keeps us healthy.
It really highlights the interconnectedness of the world and the power of physics to explain the seemingly magical.
But speaking of magic, I can't help but think back to those shattering glass scenarios.
Yeah.
Is resonance always that dramatic?
Well, not always, but there have been some pretty spectacular examples of resonance causing unexpected and sometimes destructive consequences.
Like what? Give me a good story.
There's a famous case of the Tacoma Narrows Bridge, which collapsed in 1940, just a few months after it opened.
Wait, a whole bridge collapsed because of resonance.
Well, it's a bit more complicated than that, but wind gusts at a particular frequency caused the bridge to vibrate at its natural frequency, leading to increasingly large oscillations that eventually tore the structure apart.
Wow.
It's a dramatic reminder that we need to respect those natural frequencies.
Okay, duly noted. Maybe I'll stick to shattering glasses in the safety of my own home.
I think that's a wise decision.
But, you know, all this talk about resonance and natural frequencies is making me wonder, we've talked about ideal systems like a perfect pendulum swinging in a vacuum, but in the real world, there's always friction, right?
You're absolutely right. Friction is everywhere.
So how does friction affect the motion of an object undergoing SHM? Like, does it change the frequency or the amplitude?
Excellent question. Friction, or damping as it's often called in physics, plays a crucial role in real-world SHM. It essentially acts as a resistance to the motion, causing the oscillations to gradually decrease in amplitude over time.
So a pendulum with friction wouldn't swing forever, even in a vacuum.
Exactly. The energy of the oscillations would slowly dissipate due to friction, and the pendulum would eventually come to rest.
It's kind of like the universe's way of saying nothing lasts forever. Not even those perfect oscillations.
In a way, yes, but that doesn't make SHM any less fascinating.
Absolutely. In fact, it makes it even more intriguing. It's a reminder that the world is full of complexities and nuances, and our understanding is constantly evolving.
And that's the beauty of science. It's a journey of exploration and discovery.
Well, I have to say, this deep dive into SHM has been quite a journey. We've covered so much ground, from the fundamental equation to resonance and damping, and we've seen how these concepts play out in the real world, from skyscrapers swaying in the wind to violins singing their resonant songs.
And hopefully you've gained a new appreciation for the seemingly simple but incredibly profound phenomenon of simple harmonic motion.
I know I have. But before we sign off, I have one final thought-provoking question for you to ponder. We've talked about how friction affects SHM in the physical world, but what about other systems like the economy or even social trends? Do you think the principles of SHM, like equilibrium and oscillations, could apply to these more abstract realms as well? That's something for you to explore further. And as always, we encourage you to keep questioning, keep exploring, and never stop being curious about the world around you. From the smallest atom to the largest galaxy, the universe is full of oscillations. And understanding SHM gives you a powerful lens to view it all. Thanks for joining us on this deep dive.